Heavy buildings or structures make the ground compress a little over time due to their weight. This compression of soil is known as settlement of soil. Total settlement of soil has primarily three components: immediate settlement, consolidation settlement or primary consolidation, creep settlement or secondary consolidation. The total settlement of soil is the sum of all three factors. Consolidation settlement is the most dominant factor of the total settlement. It refers to the settlement of soil that occurs because applied load causes the rearrangement of soil particles and dissipation of excess pore water pressure in saturated soils. We have learned all this in our previous video. Terzaghi gave a theory that explains the gradual settlement of saturated soils under the application of a load. The theory focuses on the process of expulsion of pore water from the soil voids, leading to a decrease in volume and subsequent settlement. Let us consider a saturated clay layer of thickness H sandwiched between two layers of sand, meaning the soil layer is surrounded by two highly permeable layers. If the soil layer had only top surface open for drainage and bottom surface supported by impermeable rock layer, water could only escape from the top surface. This scenario is known as one-way drainage. In this case, the water molecules farthest from the open surface would need to travel the entire thickness of the layer, making the drainage path equal to the thickness of the layer H. In our system, however, water can escape either from the top or bottom surface, making it a two-way drainage system. The most distant water molecule located in the middle of the clay layer only need to travel half the thickness of the layer to reach either permeable boundary. Therefore, drainage path of water becomes half the thickness of the soil layer, H by 2. When we apply a uniform pressure, say delta sigma, to the top surface, immediately after the application of the load at time t equal to 0, the entire pressure is taken up by the water in the soil pores as excess pore water pressure, or also known as excess hydrostatic pressure. This initial hydrostatic pressure, say UI bar, is same throughout the clay layer. Water begins to escape from the top and the bottom of the soil layer, causing the excess pore water pressure at the top and the bottom of the clay layer to drop to 0. However, the excess pore water pressure in the middle portion of the clay layer remains high. As consolidation progresses, the excess hydrostatic pressure in the middle of the clay layer decreases, and eventually at time t equal to T final or infinite, the entire excess pore water pressure dissipates. At this point, all the load is supported by the soil particles as effective stress. But how does this excess pore water pressure change with time and depth within the clay layer? To analyze this, Terzaghi presented his consolidation theory, which describes precisely that. Before diving into the topic, I would like to mention that if you like elementary engineering videos, you can support the channel on Patreon and get access to the questions that I have solved related to this and other topics. Also, your support will help me continue creating more such valuable content. Thank you. Now to the topic. Terzaghi developed his theory to describe the time-dependent settlement of saturated clay layers under applied loads. The theory provides a mathematical relationship between time settlement and soil properties. By plotting this relationship, engineers can visualize the consolidation process and make predictions about future settlement. To simplify the analysis, Terzaghi made several assumptions such that the soil is homogeneous and isotropic, which means soil material is same everywhere and its properties are same in all directions. Then the soil is fully saturated. Third, the soil particles and water in the voids are incompressible. Hence, when the soil is compressed, the consolidation occurs only due to the expulsion of water from the voids. Fourth, soil is compressed in vertical direction only, and with that, drainage of water also occurs only in vertical direction. Fifth, the time elapsed in the consolidation process entirely depends on the permeability of the soil. This is because there are other factors also which affects the time of the consolidation. Then, the flow of pore water through the soil follows Darcy's law, which states that flow rate is proportional to the hydraulic gradient and soil's permeability. Then, permeability of the soil remains constant during the entire process of consolidation. This assumption significantly simplifies the mathematical equations governing consolidation. Then, eighth assumption is the applied load increment causes negligible changes in the thickness of the soil layer. Though the thickness of the soil layer changes due to consolidation and H becomes H minus delta H, but the change in thickness is small enough that the original thickness H can be used throughout the consolidation analysis without introducing significant errors. This assumption implies that coefficient of permeability K and volume compressibility MV remain constant during the load increment. Again, this assumption is made because it significantly simplifies the mathematical equations. We are not going to derive the entire equation, but we will briefly discuss its derivation. Let's begin with our previous scenario where the clay layer is sandwiched between two permeable sand layers. We consider a small element of thickness delta Z at depth Z, with other dimensions being delta X and delta Y. We start with the condition of continuity of flow, which is applicable to all flow situations. This equation describes the amount of water coming in the soil element minus the amount of water going out of it. And it is equal to the change in volume of water present in the soil element. As we assumed that only one dimensional flow in Z direction, the equation reduces to this. Then next assumption is Darcy's law is valid, which says velocity of water in pores is proportional to hydraulic gradient, and that can be written as this. So our equation becomes this. Also, one assumption is that soil is homogeneous, hence permeability Kz is not changing and is constant throughout depth. So now H is the head across the soil element, and this head at any instant and at this particular depth is equal to the delta U by gamma Z. Here, delta U is the change in pore water pressure due to the applied load, or simply the excess pore water pressure at a particular time. It is also written in different books as U bar, U axis, or simply U. We are going to use a U bar here. And don't get confused this U bar or U, if it is written, with the pore water pressure. It is excess pore water pressure or change in pore water pressure. And our equation becomes this. Then for the right hand side, which represents the change in the amount of water in the soil element. We should note that change in volume of soil element is actually the change in volume of water, as solids are assumed incompressible and consolidation occurs only because of the water escaping the soil element. In our case, volume of soil element is delta V equal to delta X, delta Y, delta Z. Hence, we can write change in volume of soil element as this. Also, we know volume of compressibility is defined as this. We rearrange it and partially differentiate it with respect to time. We have also assumed that coefficient of volume compressibility remains constant throughout the consolidation process. Also, that V0 is the initial volume of the soil element, which is constant. Hence, we can write, by substituting this, equation becomes, we know at any time t during consolidation, the total stress on soil is partly carried by water and partly by soil particles, as this. And for a small change in these parameters, they become this. In our case, the total stress on soil is not changing, but effective stress and pore water pressure is changing with time. So, equation arrives at this. Here V0 is the volume of soil element, which is equal to the delta X, delta Y, delta Z. Hence this term gets cancelled out and we arrive at a very neat equation. Or we can also write it as this. This quantity is defined as coefficient of consolidation, CV, and our equation is written as this. I think some of us remember this equation very well. The equation highlights the time-dependent nature of soil consolidation, which is important for long-term stability and performance of structures. The equation is a form of diffusion equation, which describes how a quantity, in our case excess pore water pressure, spreads out over time and space. The left-hand side of the equation represents the rate of change of excess pore water pressure with time. The right-hand side shows how the excess pore water pressure changes across different depths in the soil, and that is scaled by coefficient of consolidation. The coefficient of consolidation, CV, controls the rate at which the excess pore water pressure dissipates. A higher CV means faster consolidation, while a lower CV means slower consolidation. The units of coefficient of consolidation are meter square per second or meter square per day. CV is not a constant, but while both permeability and coefficient of volume compressibility tend to decrease as soil compresses, their combined effect on the coefficient of consolidation often results in relatively stable values across a reasonable range of pressures. The solution of this basic differential equation is very simple. All we have to use is Fourier series and some boundary conditions. I guess that problem is enough for a lifetime. So we won't go deep, but would look at the overview to get a better understanding. For the solution of this equation, we begin with considering the excess pore water pressure U bar as a function of depth and time. Then we put it in the equation. When we solve this equation, we arrive at the solution where we need to get some values of quantities, and for that we use boundary conditions. Let us state boundary conditions. First condition is at time t equal to 0, that is just after the application of load on the soil, the excess pore water pressure is same at any depth in the soil and is equal to, say, ui bar, and this ui bar is equal to delta sigma. As we know, all the pressure at the beginning is supported by water only. Second boundary condition is at t equal to infinity, the excess pore water pressure is 0 everywhere, as the consolidation is considered as complete. Third condition is, at any time after the application of load, the top surface of the clay layer, that is at Z equal to 0, the excess pore water pressure is 0. Fourth condition is, at any time after the application of load, at the bottom surface of the clay layer, that is at Z equal to H, the excess pore water pressure U bar is 0. We can also write a depth Z as twice of drainage path in case of two-way drainage. Then, by further solving the equation by applying the boundary conditions, we arrive at this short and sweet equation. In this equation, this quantity is defined as the time factor. Then this equation has become even more short and much more memorable. Okay, don't memorize it, but memorize the time factor. It is a dimensionless quantity. We will talk about it a little later in this video. This solution of Terzaghi's one-dimensional consolidation equation can be visually represented through a plot illustrating the variation of excess pore water pressure with depth and time. Multiple curves are plotted, each representing a different time interval. The relative positions of these curves depict the dissipation of excess pore water pressure over time. We can observe that immediately after load application at t equal to 0, the initial curve is a vertical line indicating maximum and uniform excess pore water pressure throughout the soil layer. As time progresses, excess pore water pressure starts to dissipate and the curve becomes parabolic in shape. The highest excess pore water pressure is observed at the midpoint of the consolidating layer, gradually decreasing towards the drainage boundaries. With further consolidation, the curve flattens out and moves closer to the zero excess pore water pressure line. Eventually, when the curve becomes a vertical line, the excess pore water pressure has completely dissipated and consolidation is complete. The shape of this curve also depends upon the drainage conditions at the boundaries of the clay layer. If both upper and lower boundaries are free draining, the clay layer is known as open layer and shape of the curve will be parabolic. If only one boundary of the clay layer is free draining, the layer is called half closed layer and the shape of the curve is a half parabola. Terzaghi also introduced the concept of degree of consolidation. At any point in the soil at depth Z, the degree of consolidation capital UZ is the ratio of the excess pore water pressure that has been dissipated at that point to the initial pore water pressure at that point. Excess pore water pressure dissipated can be written as initial pore water pressure minus excess pore water pressure present at that point at any given time. It can also be written as this. This equation gives a degree of consolidation at any depth, but we are more interested in knowing the average degree of consolidation of the whole layer. So, if we substitute that massive equation and integrate it for the whole depth of the soil, we find that average degree of consolidation capital U is dependent on the non-dimensional time factor. The time factor allows engineers to estimate the degree of consolidation at any given time. The relationship between time factor and degree of consolidation can be summed up into the following empirical formulas. TV equal to pi by 4 U square for degree of consolidation less than or equal to 60%, and this for degree of consolidation greater than 60%. We have seen that time factor is defined as this. By knowing CV, we can estimate the time required for a given percentage of settlement to occur. For example, if we want to estimate the time required for a soil layer to achieve 80% consolidation, we can use these equations to calculate the time factor. Then, using this equation, we can calculate the actual time required. This consolidation analysis made by Terzaghi is very simple, but it is based on the assumptions that are not practical in the real-world situations. Hence, there are a number of limitations to the theory. First, we considered the soil as homogeneous and isotropic, which is not the case in the field. Then, we assumed that soil particles and water into the voids are incompressible. However, in reality, soil particles do compress, which is in fact the cause of secondary consolidation in soil. Then we assumed that the soil is compressed only in vertical direction and that drainage of water also occurs only in the vertical direction. However, in actual situations, water drainage and soil compression occurs in 3 dimensions. Then we also ignored the initial and secondary consolidation in the analysis. Also, the load on the soil is not usually applied all at once. It takes some time to build any structure. So, load is gradually increased on the soil. Then we assumed that the change in the thickness of the soil layer due to the applied load increment is negligible, and it was not considered. Additionally, permeability and the coefficient of volume compressibility are considered as constant, while their values change with the load increment. I would like to thank my patron for supporting elementary engineering financially. Also, if you think elementary engineering has given you knowledge that's worth something to you, consider supporting this channel on Patreon and get access to the questions and their solutions related to various topics of soil mechanics. Your support will help the channel in its journey of creating valuable content. If that doesn't resonate with you, spreading a word about elementary engineering will also be of great help. Only your love and support keeps elementary engineering going. You can find the links of books and other sources I referred for the creation of this video in the description. Read Terzaghi's Theory of Consolidation at elementaryengineeringlibrary.com. Thank you.